For more than 70 years, philosophers and computer scientists, among others, have been circling one deceptively simple question: can a machine think? It sounds like the kind of question that should have a yes or no answer. Either the machine thinks or it doesn't. Either there's a mind in there or there isn't. But the closer you get to modern artificial intelligence, the harder that question becomes. Because today's AI systems can write essays, translate languages, explain jokes, produce code, summarize books, and carry on conversations that feel, at moments at least, uncannily human. So maybe we start with the question of whether or not AI really thinks. But maybe the next question is, what exactly is it doing when it appears to think? And once we ask that, the next question becomes, is the resemblance only on the surface? Is it just fluent output, polished imitation, a statistical magic trick? Or, if we look under the hood, do we find something stranger? Little pockets of machinery that begin to resemble the way human minds work. Today on the AITEC Philosophy Podcast, we're joined by computer scientist John McCormick. John McCormick is the author of Thinking AI: How Artificial Intelligence Emulates Human Understanding, recently published by Princeton University Press. And our question is simple enough to ask, but very hard to answer. Can AI think like us? Let's begin here by talking about maybe like an overview of Thinking AI, your latest book. So tell us, what is your main goal in writing this book? Who is it for? And tell us maybe about some inspiration there from Alan Turing.
Sure. Well, it's a general audience book, so it should be fun to read and understandable by anyone. That is certainly my goal. And it addresses a fundamental question that is inspired by the great mathematician, and I guess now we would call him a computer scientist, even though computer science didn't really exist for most of his lifetime. In 1950, Alan Turing published a paper in a philosophy journal, the philosophy journal Mind, and the title of his paper was Computing Machinery and Intelligence. And at the very start of that paper, he states that he proposes to investigate the question, can a machine think? Now, he used the word machine. That was in early 1950s. Today, we would use the word computer to mean the same thing. He was talking about computing machines and abbreviated it to machine. So really what he was saying was, can a computer or can a computer program think? And that is a problem that has continued to trouble computer scientists, philosophers, cognitive scientists, psychologists, and many other people ever since the birth of digital computers in the 1940s. So clearly there's been a lot of work done on this. And the really nice thing is that in the last 15 to 20 years, we've seen amazing new developments in artificial intelligence that really help us to gain empirical evidence and understanding about this question of whether a computer program can think. So the book really has two sub-goals. The first sub-goal is to explain how these modern artificial intelligence programs work. And they're based on two pillars of technical understanding. One of them is called deep neural networks, and the other is called reinforcement learning. So the book first explains those ideas in a way that anyone can understand. And then equipped with that technical understanding, we are ready to address that classical philosophical question in artificial intelligence of whether a computer program can think, and hopefully give the reader a chance to make an informed decision about how they feel about that question based on how modern artificial intelligence systems work.
Awesome. Yeah, I would really recommend to those interested in, getting a grip on like certain key developments. Your book is really good at laying out clearly, what are deep neural nets, and what is reinforcement learning. So I just wanted to echo that. And Turing, to go back to the Turing point, I guess he kind of posed the question, like you said, can computers think? Now you kind of prefer a slightly different formulation within the book of in what ways can computer programs appear to be thinking. Maybe could you kind of walk us through the differences between those two questions, and why you prefer to ask, in what ways can computer programs appear to be thinking?
Sure. Well, there's one obvious difference, which is that second question about whether a computer program can appear to think like a human. That is a lot more nuanced than the question, can a computer program think? That immediately gets us mired down into a binary question, a yes or a no, for something which is actually a very complex question and deserves to be approached in layers with nuance. So we definitely want to remove the binary and think of in what ways and to what extent can a computer program think? And then again, take another step backwards and say, well, there's a lot of intuitive baggage associated with believing that a lump of silicon can think. We have living brains. A lump of silicon is a dead piece of inorganic matter, and it's just difficult for us to bridge that gap intuitively. So I like to just remove that whole question and just say, don't worry about whether it can truly think, whatever that means. Let's just say, can it appear to think like a human? And if so, in what ways, to what extent? Can we find some resemblances between the way this computer program works and certain brain processes that we know are going on in our own minds? And that's why I like to address this more nuanced version of Turing's original question.
Can I just kind of double click on that and make sure that listeners understand here, because this is basically key to understanding the book and basically the rest of our conversation. Let me try to say it in my own way and tell me how accurate I am, John. So it's basically, it seems like two questions. Okay, so can someone be convinced that they're speaking to something that is thinking? That's sort of one question, right? Can they appear to be thinking? Sure. But there's also this maybe more nuanced question, which is when you look under the hood, do those processes that enable this appearance of thinking actually resemble human brain processes? Did I get that right?
Yes, you absolutely did. And my response is we should be interested in all of the above. So we can take a purely what a psychologist would call behaviorist approach to this question and look only at the outputs. So if you're interacting with a computer program and all of the outputs are indistinguishable from a human, then the behaviorist approach might say, then yes, this thinks like a human, no question about it. On the other hand, many other people would say that behaviorist definition is not good enough. We do need to look under the hood and see if it's coming to its answers in the same way that a human would do it, and that the process is also important. So in my book, we do both, mostly the latter. We primarily reject the behaviorist approach, but sometimes it's good to think at that level, and especially because we are willing to take that step back, remember the gap between the lifeless silicon and the living brain, and just say, does this appear to think? Well, that might be from even the appearance, even having taken that step back, the appearance could be from a behaviorist point of view, or it could be, when I do look under the hood, does that appear to be thinking? It's still happening in lifeless silicon, so I might not expect it to be, quote, truly thinking, whatever that means. But when I look under the hood and look what the program's doing, does that appear to be resembling some kind of human brain process? So yes, you were absolutely right to just make that distinction. And I think we need to address all of those levels when we are making our personal decision of how we react to programs that have outputs that might appear to be creative, intuitive, understanding, and so on.
At this point, the conversation could have naturally gone in kind of an easy direction, right? Just yes or no questions are crude, nuance is better, end of story. But Sam presses on something important. Sometimes we really do need a yes or no answer. If an AI system were conscious, or if it had moral status, then our obligations to it might change. Turning it off, deleting it, copying it, experimenting on it, those might not be morally neutral acts. So even if John's gradual approach helps us avoid a simplistic answer, it doesn't make the sharper philosophical questions disappear.
So real quick on the whole binary question issue. So the binary question would be, can computers think? And the binary answer would be, either yes or no. And you might think that insofar, like if you connect thinking to consciousness, you might think that the question would be a yes or no. I don't know. Another one might be like moral status, right? Like if something has a moral status, you might think it's like a yes or no question. Like, does this thing have, a right to life, for example,
Yeah.
And that might seem to be a yes or no question. So it seems like sometimes a sharp yes or no question is appropriate because there is a sharp, like, yes or no fact connected to it.
Yes, and especially if there's going to be some kind of action predicated on that answer, as in, is it considered cruel and unusual punishment to terminate this program by turning it off, and questions like that. So actually, you, Sam, and Roberto are the experts in philosophy who have been studying that field for many decades. I have done my best to master the aspects of philosophy that are relevant to my book and my field, but I don't pretend to have mastered all of that literature and have good answers to these questions about moral status and consciousness. So the book doesn't address moral status at all. That question doesn't even come up. Consciousness, I mention a few times, and at one point, I basically say, okay, reader, I know that you're almost certainly dying to know whether computer programs can be conscious, so I'm going to give you what you want. I'm going to tell you what I personally think and what I think we can infer from our understanding of these modern AI systems. But personally, I think that is a rather separate question, and at least for the purposes of working with AI, not necessarily a useful one. For me, I don't really see a difference between working with a computer program that appears to think and understand like a human, but is not conscious because someone has figured out how to define that and test that. I'm talking hypothetically now. We don't have a good testable definition right now. But hypothetically, in a future world, suppose I'm working with a very advanced AI, more advanced than we have now, and it is able to give the appearance of thinking, understanding, being as creative and intuitive as any human in my interactions with it, hypothetically. And suppose, hypothetically, someone's also figured out an experimental way to determine whether that entity is conscious. If the answer is yes, I'm not sure what that tells me. If the answer is no, I'm not sure what that tells me. For the questions that I'm interested in, it's not so important. However, I don't want to just dismiss all of those other aspects of philosophy for which it would be important. It's just that I haven't addressed those and I'm not an expert on them.
Right. Yeah. And just, maybe to think about a few reasons why the more gradual approach seems fitting. Thinking, it doesn't seem to be like one single thing, it seems like it includes like language, memory, reasoning, creativity, perception, planning. So it seems to include a lot of things. And so it's really interesting to think about, AI maybe can emulate some of these better than others. So that's like one thing. And then, Yeah, and then another thing to think about too is that like human thinking seems to kind of come in degrees in some ways, in the sense of like, children, animals, experts, people with impairments. Like there's like kind of varieties of thinking there too. So that might make you think that a kind of gradual approach is appropriate in that. Anyway, I'm just kind of giving some thoughts about why, a more gradual approach.
Yes, I mean, you're absolutely right that there's a spectrum of abilities in the realm of thinking, and we have seen in the last few decades good evidence in the psychology literature that non-human animals have some kind of reasoning ability and some kind of what many people would define as a mind or consciousness. So that's indeed a level, on a point on the spectrum that is not at the level of human thinking and understanding. So, as you know, it's kind of interesting that AI programs tend to just come in at a completely different point on that map because they're so incredibly good at some things and then very limited at others. So it would be very hard to position an AI program on, say, a modern chatbot like Claude. It would be hard to position Claude on that spectrum. Like, is it more intelligent than a dog, but less intelligent than a human? I don't know, because it can do a lot of things way better than a human and way faster. But clearly, it has other limitations, as we all know. So, yes, maybe even spectrum is the wrong word, because that seems to imply a one-dimensional, tunable parameter of either better thinking or less capable thinking. Whereas, in fact, there may be a whole complex space of different abilities in thinking. And again, that is another reason to address a more nuanced version of this question inspired by Alan Turing in 1950. So that more nuanced version being, in what ways and to what extent can computer programs appear to think like a human?
Yeah, this is actually a great segue into kind of setting up the Turing test and John Searle's counter-argument, because these are exactly the kinds of questions that they were trying to, that arise from their interaction between these two. I almost want to call them traditions, because there's been so much ink spilled about these particular articles. So I think a lot of people already know what the Turing test is, but just to make sure everyone's on board, tell us, John, about the Turing test, the idea of the Turing test, maybe the original version, and also what you mean when you're going to talk about, emphasizing more so the concept of emulation.
Sure. The Turing test was part of this inspirational 1950 paper by Turing called Computing Machinery and Intelligence. And in that paper, he proposed an experiment that he called the imitation game. So many of the listeners may have heard of or seen the movie, biopic about Alan Turing called The Imitation Game. And the thing that he called the imitation game is what today we simply call the Turing test. And a modern reformulation of this Turing test would be if you were having a conversation via text message with some unknown entity. And that entity may be a chatbot, some kind of computer program, or it may be a real human. You do not know. And your objective is to somehow determine what kind of entity you are having a text conversation with. And what Turing proposed was that if you can't reliably distinguish between humans and computer programs over a large number of tests and conversations ranging over a wide variety of topics, if you're unable to distinguish between humans and computer programs, then we should simply admit that the computer program can think. So this is a 100% behaviorist test. Remember, behaviorist means just looking at the outputs and not at all being concerned with how the outputs are produced. That is Turing's imitation game, or as we now call it, the Turing test. It's interesting to note that modern chatbots, I think it's widely agreed, can pass the Turing test. The way they're set up today you can't just open up Claude or ChatGPT and do a Turing test with it, because you can just ask it, are you a human? And it will honestly reply no. But I think experts agree it would be pretty easy to reprogram ChatGPT to pretend that it's human and give convincing answers. It certainly is able to respond to an immense variety of queries on an immense variety of topics in a way that produces realistic prose in natural English. So let's at least, even if your listeners don't completely agree that current chatbots can pass the Turing test, I think they're so close that it makes no difference. And certainly we can expect that within a few years, these things will be even better. And really, if the objective was to program them to have exactly human-like conversational abilities, I think that could be achieved very easily.
Just on that note, I was going to say that I was talking to some people about this, and their objection was that it's actually in the other direction. They say it's too good. I know it's not a human because it can make a poem about, like, I don't know, photosynthesis, where every word starts with the alphabet, right? A, B, C, D, right? And obviously humans can't do that. But what you're saying is that we can take this technology, constrain it in a way, actually make it less smart, I suppose, so that it can't do these above human-like capacities. And so that's what you mean by it can pass the Turing test.
Yes, you're exactly right. So I think there are still areas where you can catch them out. And if you sort of know the tricks of how to trip up these things, you can get them to do a response that is very unlike a human. However, that is becoming more and more rare. And then there's also a question, by the way, of how exactly are you going to judge the outcome of a Turing test? Are the participants going to be experts who are trained in AI and know all the ways to trip up the system? Or is it just going to be a sort of average person brought in off the street and said, here, have a text message conversation and tell me if you think you're talking with a bot or a human? So there's many different nuances there. But to come back to your original point, yes, another problem is that these chatbots are too powerful. They can very quickly answer complex mathematical questions, come up with elaborate poems that may not be thematically and stylistically as creative as a true genius human poet, but still it can quickly produce very realistic looking poetry that is better than the vast majority of humans could produce. So yes, what I'm saying, I guess, is that you could train it not to do that, to deliberately be slower, worse, and to even make mistakes. And Turing was well aware of this, by the way. There's a really hilarious line in his 1950 paper where he's talking about, well, yes, you could just ask it to do computations, and he gives an example of a long complex addition, and then he doesn't comment on it, but if you check his math in the original paper, the solution to that addition actually has a mistake in it. So he actually put a little Easter egg in his own paper there, where people who could be bothered to check every detail would discover that he had introduced this sophisticated point right at the start, that maybe these things could make mistakes, and maybe that would actually be part of the process of proving that you're human. Or lying. Essentially, the job of the computer program is to lie about itself and imitate a human. That's why he calls it the imitation game.
Now we go under the hood. This is the most technical stretch of the episode, but the basic idea is less mysterious than it first sounds. A large language model is not a little person sitting inside a machine. At the most basic level, it is taking inputs, representing them as numbers, passing those numbers through a huge network of artificial neurons, and producing probabilities about what should come next. That can sound deflating, just numbers, just multiplication and addition. But one of the themes of this episode is that scale changes everything. When you have billions or trillions of tiny operations interacting, simple parts can produce surprisingly sophisticated behavior. So listen for three ideas: artificial neurons, weights or parameters, and attention. Those are the pieces John uses to explain how the machine moves from arithmetic to fluent language.
Many of your listeners will have heard versions of this before, but for concreteness, let me just go over the basics. So all of these large language models that we're using right now are the mathematical model that underlies the AI assistant that's layered on top of it. So the actual application that you download or interact with on the internet, which may be called Claude or ChatGPT or Gemini, for example, that is taking whatever your inputs are and sending it to an underlying mathematical model that is called a deep neural network. Now, a deep neural network is made up of typically billions or trillions of artificial mathematical models of, it's called an artificial neuron, but don't think of it as modeling a cell, a biological cell. This is a very simple thing that can take a bunch of numbers that come in, multiply those numbers by certain other numbers, add them all up, and if the result is bigger than some fixed threshold, then that neuron is going to send a message on to all of the other neurons, the downstream neurons that receive messages from this one. So you've got trillions of these things, each connected to, let's say, somewhere between 1 and 100 other neurons upstream from it. And the whole system is going to receive some data as inputs, which could be the text that you typed as a prompt. And then that's going to flow through the network. Trillions of these things are going to decide whether to send a message on to their downstream neuron or not. All of these numbers are being multiplied and added. It's just simple arithmetic. And then out pops a number at the end, which is a probability for every word that the system knows about. Typically, they have a vocabulary of, let's say, 100,000 words. For every one of those words, there's a probability of what should come next. And the large language model is typically going to not always pick the one with the highest probability, but it'll pick one of the words with highest probability. So for instance, if your prompt, and this is an example similar to one that appears in the book, if your prompt was, please give me 3 words that are related to flowers and rhyme with each other. Suppose that's your prompt. Then in it goes to the neural network. All of these trillions of calculations take place, which are all simple multiplies and adds, nothing else. And now we have a probability distribution, which might say the word mountain has a low probability. The word book has a low probability, but the word bloom has a high probability. The word rose has a high probability. And it's going to pick one of those high probability words and output that. So now we have a new text prompt, which includes your original input. Please give me 3 words that are related to flowers and rhyme. Bloom. It's got the first word of its response. We take that, put that new phrase, including the word bloom, into the same neural network. Away it goes. It does its trillions of calculations. But this time, the output probabilities will be different because it's going to be trying to find a word that is related to flowers and rhymes with bloom. So how is it going to do that? Well, there's lots of clever mechanisms in the recent versions of these neural networks. It's, by the way, the particular architecture that most of these systems use is called a transformer neural network, and that's the architecture that's explained in the book. And in these transformers, like I say, there are many important aspects to them, but perhaps the key one for us is a mechanism called attention. This is a technical term in the neural network transformer architecture. It's not exactly the same thing as a human giving their attention to something, but it reminds us of that. So what is attention? Attention is at each, at each neuron in the network, that neuron has the capability to pay attention to any other neuron at the same level in the network. So the reason these networks are called deep is that the neurons are arranged in layers. The input arrives at the first most shallow layer and then progresses through the trillions of neurons, which are all arranged in layers, until it comes to the deepest layer, which will produce those output probabilities for the different words. And at any one layer in there could be like somewhere between a dozen and hundreds of layers, depending on the architecture. But at each one of those layers, the neurons can pay attention to the outputs of the other neurons in its own layer. And this gives it a way of expressing connections between concepts. And as one simple example, going back to that specific concrete example I gave earlier, when the input prompt is, please give me 3 words related to flowers that rhyme, bloom. Now, at certain points in the network, that word bloom will be paying strong attention to the word rhyme. And this is likely to trigger other neurons within that network that in the huge bulk of training data that this architecture was exposed to when it was trained, which is basically the entire internet, every book that was ever written, and a bunch of other stuff that these companies have been able to get their hands on. Based on everything it's seen, there will be a neuron somewhere in there that fires when there's combined attention on the concepts of bloom and rhyme, and also flower, but especially bloom and rhyme. And then that is going to naturally, there's no sort of homunculus in there saying, oh, this means rhymes with bloom, therefore we need, now I'm struggling to think of an actual word.
I think in the book you said gloom next, right?
Yes. Okay. I was trying to avoid gloom because of the confusing fact that it does not immediately make you think of flowers. But let's go with that, and I'll explain afterwards why gloom actually is often associated with bloom. Yeah. So gloom does at least rhyme with bloom, and that will get a high probability. And if it's sufficiently high, that could be chosen as the next output. Yes. And so parenthetically, in case listeners are wondering, why on earth? So this is a real example. I mean, I did it on an earlier, simpler example of the family of GPT models. I think it was GPT 3.5, where this exact experiment was done that appears in the book. It turns out, if you go and look on the web, the words bloom and gloom do actually have fairly close associations, because there are lots of articles and advertisements that say things like, oh, remove the gloom of your day with some blooms. And therefore, those two concepts do get an association in the real world. And that is something that the model has picked up on.
I wanted to mention something about the feeling of reading your book, which is kind of an interesting idea. But I remember so you explain wonderfully all these processes. You explain the difference between a biological neuron and an artificial neuron, and then obviously the biological networks and the artificial networks. And as you're learning the mathematics of just so that everyone knows, the mathematics are very simple. It's like just multiplication and addition, basically. What gives the software its surprising power is the scale, right? I mean, just no human, no human consciously would want to, multiply and add all these numbers together.
Mm-hmm.
So there's if there's like a trillion neurons, there's roughly a trillion connections, right? I guess.
No, there's actually something like every neuron has, in our human brain, we have about 10,000 connections for every neuron. In the computer models have not got to that level yet. That is just a vast number of connections that are not supported even by the most fancy GPUs and hardware that have been produced so far. But depending what kind of task it's doing, I would say you could see maybe hundreds of connections going into a single neuron in the transformer neural network architecture. Yes. So in terms of what are the kind of settings that makes this all work, it's what we call parameters in computer science. You can imagine that every one of those connections between neurons has a number associated with it. And that number, we call it the weight, but it's really how much importance does this connection have? And that's the thing that's going to be multiplied. So when the connection fires, a signal arrives from the upstream neuron, it's going to be multiplied by the weight that's sitting there on that connection, which could be, I don't know, plus 10. That means the signal gets multiplied by a factor of 10. Or it could be minus 1, which means it gets negated and it's actually going to reduce the chance of the downstream neuron firing. But yes, so we have all of these trillions of neurons. There could be hundreds of trillions of connections. If each neuron has 100 connections, we're just throwing out numbers here. And yes, there are, therefore, in that particular network, there will be 100 trillion parameters that are affecting the output.
Mm-hmm. I just wanted to mention one more thing here about the technical stuff, and that's the backpropagation. I feel like that we need some good visuals around this, because it just goes through a bunch of computations, and then based on the output, it'll get either flagged as that's a good one or it's a bad one. And if it's a good one, it'll go back. That's where the backpropagation comes in. Go back in the network and kind of strengthen those connections that led to the correct output. Did I get that right?
Yes, you did. Okay. So yeah, this is kind of interesting. So one of the things you said earlier was the mathematics of how these transformer networks produce their outputs is amazingly simple. In the way it's explained in the book, a few of the bells and whistles are eliminated. So it's not literally this simple, but the most important features are just multiplication and addition. So yes, literally the numbers come in, they're represented as numbers. The inputs come in, they're represented as numbers. So you can think of every word in English, like the 100,000 words in English, each having a number that codes it. And those are the things that actually come into the network, because everything is dealt with as a number. And then from that point onwards, all we're doing is multiplying signals, which are numbers, by the weight sitting on the connection, and added those all up. And if it's bigger than a certain value, send the result on to the downstream neurons. So you are absolutely correct that this is a very simple process. The process of training the neural network in the first place uses more complex mathematics, but not irretrievably complex. And in fact, in the book, I hope I was able to give a reasonably good flavor of how this works. And so let me have a go at explaining that now, even in the audio-only format. I think we can get some idea of what's going on here. So when you train a neural network, the objective is to set all of these parameters. Remember, each one of the connections has a number sitting on it that we call a weight or a parameter, and that's going to determine how much importance signals going through that connection are given. So what we can do is, let's, for example, say we are trying to train an object recognizer. So this is going to be a visual recognition system. We present a picture at the lowest layer, the shallowest layer of the deep network. And the picture has information about all the colors at each pixel, which are translated into numbers. And so we have these numerical inputs coming in. And then that flows through. Initially, this is going to sound horrifically unscientific, but this is the state-of-the-art way that a professional will initialize the parameters of a neural network. They'll choose a bunch of random numbers. So initially, all of those parameters have random values. We send the first picture through, and it's going to produce a completely nonsense result, like reindeer, when in fact, it was a picture of a suspension bridge. But what we can do now is we can say, oh, this is what we call labeled data. So I'm going to tell the computer system what it should have done. I know this is a suspension bridge and not a reindeer. Therefore, please go to the probability that you just output for suspension bridge, which may have been 0.0001, and adjust all the parameters in the system in such a way that that gets increased a little bit. You might wonder, why don't we just change them all so that the suspension bridge goes up to probability 1 immediately? There's technical reasons not to do that. We have to adjust this system gradually. But what we do is we make small adjustments to the parameters so that instead of being 0.0001, that probability for the suspension bridge is now maybe 0.001. And then each time the system sees that picture of the suspension bridge, it might see it many times while it's training, even though there are millions of other images also. Each time it sees that, the probability of the correct output is going to increase a little bit, because you can think of these parameters as little dials that get adjusted. And we just make small adjustments to gradually move the network parameters to values that produce good, accurate answers on as high of a percentage of the training set as possible. Now, why is it called backpropagation? This process of twiddling the dials on the parameters so that we can slightly increase the probability of the correct answer. The reason is that when you do it mathematically, you need to start from the deepest part of the network and work backwards. So what we say is, I want the probability for the suspension bridge to be a little bit higher. Therefore, this parameter should have been a little bit smaller, this one should have been a lot bigger, and this one should have been a little bit bigger, and so on. And then we say, well, for those parameters to have those changes, we look in the previous layer and say, that means these parameters should have been adjusted in this way, and so on. And we work backwards, computing the changes that are needed at each stage. And this technique of backpropagation has been reinvented and rediscovered several times in the artificial intelligence literature. The person that most often gets the credit for discovering it, and he did independently invent it, it's just that he may not have been the first person to do so, is Geoff Hinton, who not only won a Turing Award, the highest award in computer science, for his contributions to artificial intelligence and neural networks, but also they threw in a Nobel Prize in physics. So the physicists were so impressed at his work in neural networks that they also gave him a Nobel Prize.
At this point, John has walked us through the basic machinery: artificial neurons, weights, probabilities, and the process called backpropagation, where a system adjusts itself after getting an answer wrong. That can make AI sound almost disappointingly mechanical. A picture goes in, numbers move through the system, the output is wrong, the weights get adjusted, try again. But now comes the deeper question. Human beings also produce fluent language. We also recognize faces. We also connect concepts. We also learn from correction. But from the inside, we don't feel like probability machines. We don't experience ourselves as adjusting thousands or millions of little dials. So, is the similarity between AI and human thinking only at the level of output? Or are there deeper analogies hiding inside the system? That's where Sam picks the conversation back up.
Yeah. So, okay, that's really helpful. So the system, it's not just kind of producing probabilities, during training. It's also being corrected through like backpropagation, starting from the error and the output, and then, kind of working backward through the network and making like tiny little adjustments, like you said. So I guess that raises the question with kind of human thinking. So, from the inside, it doesn't seem like we're calculating probability distributions over thousands of possible next words or whatever, or adjusting all these parameters, right? So you might think that the similarity to human thinking is merely at the level of output. Both us and ChatGPT produce fluent language output. So I guess my question is, do you actually think that there might be a deeper analogy, not just the output analogy, but maybe there's something deeper going on in terms of the underlying process? Or so what's kind of your position on that?
My position is yes. I think we can point to similarities within these deep networks and the human brain. It's going to be at the level of little pockets of similarities. We can think of them as circuits. I'm not using that in a technical, in a rigorously defined technical sense. But when I say circuit, I just mean a little part of a neural network or a little part of the human brain. And for large language models, I think we still don't have, or at least at the time the book was written, we didn't have great, hyper-convincing examples of similarities. So in the book, what I have is the example of these attention values that are calculated between pairs of neurons at the same level in the network. And those, at a high level of analogy, I think it's reasonable to say this is a kind of way that network is able to connect abstract concepts to each other, which may resemble the way that we do it in the human brain. I'm not saying that the human brain uses attention scores. I am saying that somehow the brain must have an ability to connect concepts and produce new associated concepts that relate to the original ones, and that the attention scores in modern transformer models, in some sense, capture that same ability. So this actually links into a concept called emergence that we may come onto later, but I'll leave that there for now, because the thing I do want to mention instead is to go back to the visual recognition problem. Because we already have more than 10 years of experience with those models. The visual ones were the first ones to make a real breakthrough in this new revolution of AI that involved deep neural networks and reinforcement learning. Those networks were the ones that first really cracked an AI problem that had previously been thought to be essentially insoluble. For example, in my own career during the late 1990s, I was working in grad school on certain aspects of computer vision, getting computers to analyze images. And I didn't directly work on object recognition, but I knew people who did. And that was just considered a problem that would take many decades to solve and was extremely intractable. And we were chipping away, like making these tiny little progress, getting the success rate up from 32% to 32.5% on some pretty small database of objects. Whereas when Hinton and his folks came along in the 2010s, they were able to train up on this image recognition challenge called ImageNet that contained 1,000 different categories of very specific things, like the suspension bridge I mentioned earlier, but also duck-billed platypus, wheelbarrow, nurse, cowboy hat, lots of very specific breeds of dog, golden retriever, some specific type of spaniel, I can't remember what, that kind of thing. So 1,000 categories, they got to train on about 1 million images, so plenty of examples of each category, and then test on 100,000 images that the system had never seen before. So brand new images that it has no advantage on. And I don't remember the exact results, but they were able to achieve very high accuracy, significantly higher than any previous system, by using a deep neural network. So let's talk about some potential similarities in that kind of visual recognition system with the human brain. What we find is, if we look into one of these systems trained by Jeff Hinton and his collaborators, and we start looking for neurons not at the very deepest layer, because that layer is the thing that outputs a probability for suspension bridge or golden retriever. We look somewhere in the middle. And if we look at a few neurons, eventually we'll find ones that respond to certain types of inputs much more strongly than others. And for example, as you can see in the book, there are actual outputs reproduced there of the image patches that produce strong responses at one particular neuron about halfway down the layers. And what this neuron responds to is regions of an image that contain a face, a human face. So this is really amazing, because nowhere in the training data is the concept of face presented. There is no object category in those 1,000 object categories. There is no category called face. All of the objects are much more specific and contain multiple parts, whereas a face, in this context anyway, is always part of a larger object like nurse. So therefore, what has happened here? what has happened is the network has spontaneously somehow, and I'm going to use some anthropomorphic language here. I don't want to push it too hard. It's not like I believe there is some human-like figure in there guiding it, but I'm going to use the word realized. The network has somehow realized that it's useful when trying to recognize cowboy hat, for example. It's useful to be able to recognize a face, because very often a picture of a cowboy hat, it's being worn by someone and there's a face immediately below it. So that's one of the clues that the thing you're looking at is a hat, if you can see a face below it. And you can imagine dozens of other examples where it might be useful to be able to recognize a face because it gives you clues about the other bigger objects that are present in the image. So we found a face neuron there, and you can see the actual outputs in the book to convince you of that. We found other neurons that respond strongly to, for example, the heads of animals with floppy ears. So this is a very bizarrely kind of specific thing that you might not think you have a neuron in your own brain that responds to heads of animals with floppy ears. But I would actually be willing to bet you do. Somewhere in those trillions of neurons of yours. Anyway, definitely in the network that we were examining, there's a neuron that responds just to those heads. And of course, again, there's no training data that has the concept of ear or floppy ear or head with floppy ear. This is something that the network has somehow, quote, realized it is useful to have for recognizing various breeds of dogs that also have floppy ears, like spaniels. So we found a neuron that for the floppy-eared heads. We also found another neuron for pointy-eared heads. And of course, that neuron is useful for recognizing things like foxes and cats. So this is really quite remarkable. And I think this is a very inspiring connection between the way that deep neural networks are able to produce results on AI problems and the way that human brain processes function. I won't go on about it now, but there are other experiments in the neuroscience literature demonstrating that humans do have these same kinds of neurons that can recognize specific objects and parts of objects and other low-level concepts that can be combined to produce a high-level inference.
Notice the move John makes here. Instead of claiming that the whole AI system thinks like a whole human brain, he makes a more modest claim. Look for pockets of resemblance. Look for small circuits, small patterns, small functional similarities. And to make that case, he turns away from language for a moment and toward vision. That might seem like a detour, but it gives us one of the clearest examples in the episode of something genuinely surprising. An AI system developing internal features it was never explicitly taught. Not just memorizing labels, not just matching surfaces, but discovering useful structure.
So just to echo real quick what you were just saying, John, like, so it's really important that the network is not just like memorizing labels or like matching surface images. It's discovering kind of useful features somehow that were not given in the training data. And I mean, you mentioned emergence earlier. I mean, the concept of emergent AI is really one of the key concepts in your book. Would you want to maybe unpack, like this would be an example of emergent AI for you, right? And maybe you could define that.
Yep. So the concept of emergence itself is just the fact that we observe in the world systems made up of a large number of small, simple interacting components. Systems like that can often produce qualitatively new, interesting, definable, observable behaviors and properties. And the simplest example that's often used is that of a copper wire. It's made of many trillions of identical copper atoms. This wire has a macroscopic property that it can conduct electricity. It has conductance. It has flexibility. You can bend it. But if you look at one atom, that can't conduct electricity. That doesn't have any flexibility. Doesn't even make sense to consider those properties. So emergence is a very obvious, natural thing in certain situations, like that copper wire. But we can also apply it to things, excuse me, such as the human mind. So many people would agree that the human mind has reality. It's a phenomenon that we can investigate, discuss. It has properties. It's a real thing. But where does it come from? Well, I and many others would say it's an emergent property. So there's no mysterious mechanism operating inside your head. All of the neurons, we have a pretty good understanding from neuroscientists of how those neurons individually work. They're all connected to up to 10,000 other neurons sometimes. And by interacting, this large number of relatively simple components somehow produce the emergent property of a mind. So that's emergence as it occurs in biology. What about in a computer program? Well, the terminology that I use in the book is to apply this word emergent to human-like behaviors that we can see in these networks. So I would say that the neurons that spontaneously became able to recognize faces and pointy ears without ever being specifically trained to do that are an example of emergent recognition. Somehow the training process with its millions of iterations and the artificial neurons in that network with their millions of interactions have produced an emergent property, which is the ability to discover a new feature, that of the pointy ear or the human face, and to successfully recognize it. So that's emergent recognition. The book also has examples of emergent understanding, emergent thinking, emergent creativity, and so on.
So far, the conversation has moved from the outside of AI to the inside. The outside question is Turing's question. Can the machine produce behavior that looks intelligent? The inside question is John's question. When we inspect the machinery, do we find processes that resemble parts of human thinking? But now we arrive at one of the most famous objections in the philosophy of artificial intelligence. Even if a machine produces fluent language, does it understand anything? Or is it merely manipulating symbols? This is a challenge raised by philosopher John Searle in the Chinese room argument. And in a conversation about modern AI, the Chinese room becomes newly strange, because the question is no longer just whether a rulebook can imitate understanding. The question is what happens when the rulebook is replaced by something like ChatGPT. All right, let's see. Let me try to summarize for you John Searle's Chinese room argument, and I'll hope to highlight all the things that you want to talk about. What he does is provides a thought experiment where he gives a way to demonstrate that it doesn't seem like computer programs really have any real understanding of what's going on. And so he imagines someone in a room, he calls it the Chinese room, and this person is speaking with a Chinese, someone who is competent in the Chinese language, maybe a native speaker, and they're getting notes through, let's just say, under the door, right? And so the person inside the room is getting these notes in Mandarin, and they have a rule book or a ledger or whatever, so some book there that kind of instructs them. If you see these symbols in Mandarin, even though the person in the room doesn't know Mandarin, they are able to, through the rule book, figure out the appropriate response to slide back under the door. And so John Searle's point here is that obviously the person inside the Chinese room has no idea what's really going on. He doesn't know what the conversation is about in Mandarin. But to the person outside the room, they feel like they're having a fluent conversation in Mandarin. And so for this reason, the same thing is happening with the computers or computer software. It might seem like it understands, but really it's just engaging in formal processes, and it doesn't really know what's going on. Did I capture all the elements that are important to your argument, John?
Yes, absolutely. So the place where the book would pick that up is to say, it is obvious that I call that person in the room the human subject. And I think of the people outside the room as the experimenters. They're trying to do an experiment to see if whatever is behind that door can understand Chinese. That's what they want to know. And we all agree that the human subject cannot speak Chinese, does not understand any Chinese. All they can do is follow instructions written in English and laboriously copy Chinese characters that are in the instruction manual without understanding what they mean. So, yes, I mean, Searle's basic point is there's no part of this system that understands Chinese. Clearly, an inanimate instruction manual can't understand Chinese. We all agree that the human subject doesn't understand Chinese. So, no, there's nothing that understands Chinese here, even if the behaviorist approach would say, the system's producing perfect Chinese, we must declare that it understands Chinese. So what if we take that instruction manual and replace it with a computer? And in modern times, I mean, Searle didn't have access to this, but in modern times, we could just give it an internet connection and let it use ChatGPT or Gemini to produce appropriate responses from the Chinese inputs. So now the human subject is reduced to doing almost nothing. I mean, if they're receiving pieces of paper slid under the door, I guess they have to pick up the paper and maybe hold it up to the camera on the computer, because optical character recognition is also very good now in these AI models. So it can probably just read it by holding up the piece of paper in front of the camera, produce an appropriate output, print that out, and the human subject just is literally shuffling pieces of paper and doing nothing. And so now our intuitions are going to respond quite differently to this whole system. Again, everyone agrees that the human subject doesn't understand Chinese. But what about the computer, or what about the AI system that's producing these outputs? It's a lot less clear. And depending on how much we look under the hood and how much we're willing to take a behaviorist versus more internal-based approach here, we might agree that there's some kind of phenomenon here that we could label as emergent understanding. So rather than just saying it's true understanding, because I find that actually a difficult concept to even define, let's just use a different label. We could use artificial understanding or emergent understanding, which emphasizes the fact that this understanding has emerged from the complex interactions of those many artificial neurons inside the large language model or the transformer model. And yes, so I think this is an interesting new challenge to Searle's thought experiment, because now that we're armed with programs that can do such good machine translation and natural prose responses to questions, I think that really starts to push our intuitions closer to thinking that there is an aspect of this system that has emergent understanding. It may not be the same type of understanding that humans have, but it is a phenomenon worthy of study, and it is a form of understanding. So we can push it even further, but that's one point at which we, readers and listeners can decide, like, what level of comfort do you have with this approach? Are you willing to grant that there is a phenomenon going on here that is some kind of understanding? And would you be comfortable calling it emergent understanding?
This might be the part where I put my foot in my mouth a little bit, speaking to a computer scientist here. But Sam and I have been interviewing many people about large language models and their capacities and their limitations. And so let me, kind of run this idea by you and kind of get your response. One might feel that, large language models, maybe because they can't engage in causal reasoning, according to some people, or maybe because they're still so prone to hallucinations, or they can't respond to anything they haven't been trained on, or for, reasons X, Y, Z. There is some limits there that might make it so that large language models are not really, sufficient to get at real emulation of human thinking, since human thinking does have causal reasoning, for example. But do you think that even this line of argument will eventually be, rebutted by new hybrid models, where we take a large language model and I don't know how to connect it with some Bayesian networks and a world model and whatever, right? Will there be new hybrid versions of AI models where it would be increasingly difficult to sort of make these arguments?
I would actually approach that issue another way. I mean, certainly I think there are going to be new architectures, and who knows what the next big thing is going to be. Maybe it will be a new architecture of neural network model. Maybe there'll be some completely different thing that comes along and is even better. I'm actually crossing my fingers that doesn't happen anytime soon, because I don't want my book to go out of date, within 2 months of it being published. I've made pretty strenuous efforts to future-proof this book, in the sense that all of the examples I give are evidence of emergent thinking, emergent understanding, emergent recognition. It may be that next month someone comes out with even better examples of those phenomena, but this book still puts a stake in the ground at a certain point in this AI revolution and shows, look, even now we can see these glimmers of circuits in the deep neural networks that have similarities to circuits in human brains. And that's where I would stop my strong claims at that point. So I'm not trying to say that LLMs as they exist now understand English or understand natural language perfectly. That's absolutely not the case. And specialists know how to catch them out and trip them up, cause them to hallucinate, cause them to make false statements. So that's not the case. But what I hope the book does is point out some examples of some aspects of these models that have resemblances to human brain processes. And we can expect that as these models get bigger and more sophisticated, or maybe completely new things come along, that the match between how many of the circuits in the AI program have similarities to those in the humans, it may increase to be increasingly similar, or maybe it will diverge, and we'll find that, in fact, it's much easier to write AI programs that work in this completely different and clearly non-human way, but is still useful for humans. Of course, I can't predict that. But there's another angle of the book that we haven't talked about at all yet, which is fairly early on, I go through an argument about brain simulation computer programs. So computer programs that literally try to emulate the inputs and outputs of every neuron in a human brain. That's far beyond our capacity to scale right now, but there has been a lot of progress in brain simulation. And for example, the entire brain of a fruit fly was mapped as of a couple of years ago. And, we'll keep making progress from there. So I believe, and I think the book explains, that it's very plausible, and that I hope most people would agree once reading the arguments, that it's possible in principle to simulate a human brain. Just take all the connections between all the neurons and calculate what would the outputs be given these inputs. And hey presto, here we have a computer program that is producing the same outputs as a human brain given the same inputs. And so this, imagine you get that program and put it into the computer in the Chinese room. Now, are you going to credit that with some kind of emergent understanding? It's literally emulating a specific human brain that's been scanned, and we know all the ways that the neurons work, and we're simulating them with enough precision that it produces the same outputs. It's not going to convince everyone, but I think at this point, many people would be willing to at least adopt some terminology of saying, yes, it's emulating understanding. It's producing the exact same outputs as what a human brain would in that situation, and therefore it's emulating the understanding of Chinese that the real brain clearly produces. So that's one angle of the book, but I don't like to lean on that too heavily because this whole brain simulation thing, number one, it's pretty impractical. It can be done in principle, but to actually do it in practice, I don't know if that's ever going to work, and it certainly would be a long way in the future. I think it's more productive and interesting to look at real AI programs that have been developed and try to understand which aspects of them resemble some human processes and to what extent. And that helps us answer that original question in the book of in what ways can a computer program think like a human?
There is an anxiety underneath all of this. If machines can produce language, solve problems, recognize patterns, imitate creativity, and perhaps even develop forms of emergent understanding, then what is left for us? That question can sound threatening, but John's final answer is not nihilistic. It is, in a quiet way, humanistic. Even if intelligence is not ours alone, human life is not exhausted by intellectual performance. We still have relationships, humor, grief, ritual, love, the strange texture of living a life from the inside. So the episode ends not with a declaration that machines are human or that humans are machines, but with a more generous possibility. Maybe intelligence was never the only thing that made us worth caring about. John, is there anything we haven't asked you yet that you want to add to the conversation?
Well, I guess we didn't really talk about the implications of this for humanity. If we accept the hypothesis that computer programs can equal or exceed humans in all of these intellectual arenas, such as creativity, intuition, thinking, understanding, what's left for us humans to do? Some people might get a kind of nihilist feeling if we're forced to accept that hypothesis. And so towards the end of the book, I try to put a positive spin on that. I certainly am very optimistic and positive about this. I'm quite happy to accept that human brains aren't the only thing in the universe that can do sophisticated computations and understand things like natural language and possess creativity. I'm quite happy for other entities out there in the universe to do that, and I'm happy for some of those entities to be AI programs that we've built on this planet. That doesn't bother me at all because I'm going to continue to have relationships with other human beings and to enjoy things like jokes. I'm going to laugh. I'm going to cry. For those who receive fulfillment from religious practice, they can continue to practice religion and receive fulfillment from that. I don't see any of that as being in conflict with the fact that we also have these entities in the world and some hypothetical future world that exceed us in all intellectual realms. So I'm positive about that. I think while there are dangers and potential problems with AI, I'm optimistic that we can avoid catastrophic outcomes and that overall those entities will tend to improve our lives rather than harming them, and that we can continue to enjoy our own humanity.
That was computer scientist John McCormick, author of Thinking AI: How Artificial Intelligence Emulates Human Understanding. Today's conversation began with Turing's old question, can a machine think? But maybe the better question is the one John leaves us with. In what ways can a computer program appear to think like a human? And what do we discover when we look under the hood? For the AITEC Philosophy Podcast, I'm Roberto Garcia. Thanks for listening.